Okay, hello, back again to our statistics lecture, and we started last time a new topic, and this is, in general, easy methods of forecasting if you have a time series, if you have the development, so to speak, for profit or for revenue in your company. And in this case, data, maybe look like this here. So this is our original data. And within this original data, we, maybe can identify different components. So if we look at this data set, then, and this I would always recommend that at first just plotting the data and looking at the diagram you get out, because then sometimes directly you have some clue which kind of components you can find or maybe find in the historical data. And if we look at these data set, then of course in general we could say that maybe we see that in general the revenue data is going up during time. And this should be hopefully the case if you are managing your company. But also we see that around these general trend, we can maybe identify some cycle, and then we are quite interested in the period of this cycle, of the frequency of this cycling data, because then we can say, well, maybe we are here in the upswing or in the downswing, and this is of course also for strategic or operative decisions within your company very interesting. And then we can maybe say, take me this out again that you can see this better, that maybe we see here some within a year repeating data, so that we are always going up, going down, going up, going down. If we interpret here time t maybe as monthly or quarterly data. And then of course, since we don't know everything about the future, there will be mostly of course also some random component. And these four components I plotted for you here. So this would be then, without this cycling, without the seasonality, without the random component, a straight trend of constant growth. This would be then the cycling data, and this the seasonal data, and then of course in the end we will have a random component. And last time then, as an example, as an exercise, we created such a time series the other way around. And let me see that we also go in this one. There is my Excel sheet. Did you see it? No, this is the other one. This is, where have I, so I have my data set. No, didn't I save this? Well, I have to look at it. Anyway, we did it the last time. So we started with creating a trend, then with our cycle data, then the gray line with our data of the seasonality, and the yellow one, the random component. And then in the end, when we just added up all these four components, then we created these data set of a total development of maybe revenue, profit, or anything else you can economically think of. And of course, maybe you have already seen this, actually also in macroeconomics, that if we take, for example, unemployment data for Germany, which shows actually in reality such a pattern. So here we have maybe something like the business cycle going up here, of course, meaning the other way around, that it is bad, but this one going down in unemployment, this would be then the good part. And we also see here our seasonality, and of course there will be also a random component. Okay, but then we will go to some possibilities how we can make then a forecast having the historical data. And for this, we will use here another data set. And with this, we started. So this should be revenue during the last years. And we should have here quarterly data, Q1, Q2, Q3, Q4. And what we are interested in is then a forecast for the first quarter 2023, or a forecast for the whole year of 2023. And this one here, I think I have my Excel sheet for this. This is now my forecasting. There it is. And we started the last time just with plotting this data set. So let me move it here that you see everything. And now it was a growth example. Well, then again, let's put it from here. Revenue data. And the other part. And plotting it. And then it looks like this. So, and also within this data set, we also see here some general trend going up. and maybe also some seasonality since we have here only quarterly data. Well, if we have here really a cycling component, looking just at the data, I would doubt it. But of course, there will be also some random component. Well, and now we want to start that I will show you some different methods of forecasting. And the simplest forecasting is, of course, just looking out of the window and saying, my best forecast is for the weather tomorrow is the weather today. This seems very naive, but if we think about it economically, then of course we have also to admit that if we think of totally competitive capital markets, then of course from a theoretical standpoint, the best forecast for tomorrow is the last value of today. So in then expected value t plus 1 of x is just xt. This is the so-called efficient market hypothesis. Did anybody of you already heard about these efficient market hypothesis? So if we assume that we have totally competitive capital markets, because in this case we really assume that, for example, stock prices are just following a random walk. Then, for example, stock prices are following a random walk. Anybody heard of this? Maybe if you have heard some lectures in investment or something like this? No? Well, I think this you should know if you are studying economics. Well, of course, but this is only a very simple method. But sometimes, if you take the framework where you are in, then it is maybe also a good way to forecast your data. So then let's take as a first shot the so-called naive forecast, and let's take here 2023 and Q1, and in general we want to forecast the whole year, and Q2 and Q3 and Q4. So the naive forecast would be then here just the last one here. Okay, but then of course we also have other methods, and another method would be the so-called moving average. And for this, actually, if we look at this data set, then we see here that we have maybe here something like this seasonality. And then, of course, when we would make our forecast, the naive forecast, just in the upswing of this seasonality, then our next value will be in general a higher one compared to the case when we are in the downswing of our seasonality. And for this, in general, we would then look some more periods in time backwards and just averaging these values using the arithmetic mean and using then this value in order to forecast the next period. And for this, maybe we could say, let's say we are taking the average of the last 4 quarters, because maybe we have identified here that every 4 quarters we have a repeating pattern. And so then our next forecast here, moving average with n equals 4, would be just the arithmetic mean of these 4 values. So taking this moving average, and let's say with n equals 4, and then it would be the mean of our last 4 values. And of course, then we see we have just also incorporated these lower values within our seasonality component. Okay, but also we could, of course, smooth our data set in general using these moving average method. And this means also that we in general want to get rid of the pattern we have here that we are going up and going down. Well, then of course we also have, when we are taking the average of more periods, that we then have to set our averaged new data point with respect to a specific old period in time. And for this reason, we quite often use an odd number averaging the old data, because then we can just identify the new value with, so to speak, the middle of our averaging period. So if we have, for example, if we take, for example, n equals 3, what we then will do is that we identify the starting from t is 0, t equals 1, t equals 2, then we will identify the new created data point with t equals 1. So always taking just the middle where we are averaging. And this we will do here. There we will just create a new data set. Then let me move in moving oops, average data. And let's take, for example, t equals 3, n equals 3. And what we are then doing is here, so the second data point, we create a smoothed new time series identifying for 2018 second quarter now the average of these three values. So here we're using then 330, 45 and 90, and this will now our new data point with our smooth data. And then of course we can just move these formula going on in time. So these 363 is then just the average of these three values. And clicking inside here, we see, of course, this is the average of these three values. And so we just copy this down here. But of course, we cannot copy it just at the end of our data set, because then we would move out of the range with our averaging process, because for 2022 Q4 we would also need, of course, for the averaging process the data point of 2023 Q1, which of course we do not have, so we have to end up here. And this would be then our average data. And let's have a look how does this data series look like. So we add this data series. This would be then our moving average, and copying this hopefully works. Okay. And now you see here that of course your new data set doesn't have these high maxima or low minima of this seasonality. And so this is a possibility to identify more or less this trend component which we were talking about. And of course, this we can change. We can not only use n equals 3, but also n equals 5 or 7. Let's also take the n equals 5. And I insert again a new column, taking n equals 5. But if it now taking n equals 5, then this will mean that we are starting with the first 5 values here, averaging this, and now again taking the middle. And taking the middle would be then that we start with the data point of smooth data in 2018 Q3. So oh no, this is wrong. There we have to take 1, 2, 3, 4, 5. And of course, then we can create again a smooth data point, but of course then we are moving, unfortunately, and this is a yeah, one drawback of this method, then we have to move back in history now to 2022 Q2, because of course again we need 5 data points of the original data in order to average. Okay, so let's also add this new time series in our diagram. I'll do this one, and can here, if we change this one a little bit from 300, that we see a bit more, and this one. Let's go here. Okay, and of course we need here n equals 3, and we need here to identify it in the right way, n equals 5. And now of course you see that our gray line with n equals 5 of course is much more smoothing our data. And this is actually a method which is quite often used in practice. Again, a question: did you have used or seen in other lectures already the method of moving averages? Because when I studied, we did this, for example, in a marketing lecture or in a planning and organization lecture in business administration. Because this is maybe the simplest forecasting method which is maybe always used in companies and enterprises to make a first shot. Where are we and where will we in the future? Where will we be in the future? Feedback from you, please. You really haven't seen moving averages before? Well, anyhow, then it is like this. Okay, so here we can then, of course, use these methods. One is, of course, the knife, and I also recommended to take 7. Okay, then in order to be what I ask you in this little exercise, then we also want to create the last one. Oh, sorry. N equals 7. And then, of course, we have to move one step forward, and 1, 2, 3, 4, 5, 6, 7. Closing and going to the end. And this would be then our last one. This one copying this, and then we will have 7 and we should also make the forecast with these values. So we would have then n equals 3, 5, and 7. And using these values would be then for 3, 515, and for 5 we will have 478.8, and for 7 n equals 7 is 471. Here, and this these values, of course, we could then use also to create maybe a scenario of our time series, and for this we actually can add these forecasted values just to our time series here, and therefore we copy our data set for, and let's see, then we use, this would be actually n equals 1, and use this one and putting this down here. Then we are cutting, or at first let's put this one here, and then we are cutting all this data. This we don't need, and then we are moving this up here, and then let's split our data set here. Actually, we can just add all these data, doing it in this way and creating a new diagram with all our different forecasting methods. And again, in order to see our different scenarios of forecasting, 300 to 55, let's say. And up we are. So here we are. This would be then forecast. And here you see our different methods of forecasting. Let's take also here 2023 Q1. And well, when we want to see it in a better way, we can also shorten our time series. And or I think the best way is just clicking inside, and then you can shorten your data set with this. And let's say we start in 2022 and manipulating our starting point would then mean that you see here your different scenarios for a forecast. And this is also quite often made when you are presenting data that you are doing different scenarios. Okay. Well, forecasting with moving average, what do we have done? Why we are doing this process? Because of course we have not anymore these jumps in our data, especially we can smooth our data from this seasonality or cyclical components. But of course, using these moving averages, because we are only look backward and we do not make assumptions about the future, then we are more or less setting on the level of the last periods of n equals 3, 5, or 7. And this, of course, where we have in general an increasing trend, and if this increasing trend would also go on in the future, taking just the average of the historical data would then mean that we take out this increasing trend. So we have to keep in mind, if we look at our data and we identify this increasing trend, that then using the method of moving average would in general underestimate our data. And of course, in the other way around, if we would have a decreasing trend, then of course we would have an overestimation of our data. And of course, smoothing our data would then also take out the seasonality effect. Of course, this is maybe what we want to do, but the other way around, we have to keep in mind that within our data we have the seasonality, and therefore if we just make a forecast for the next quarter, then maybe we have to redo the calculation for the seasonality. And this we just have to keep in mind, but this is always the case if you are averaging the data of your data set, that you are losing some information of your data set. But as I said, this is very, very often used for strategic or operational decisions within a company. Okay, then we will go further. As we said, we have taken out this trend by averaging just the last data points. We can use another method which is called exponential smoothing. And yeah, this is maybe some generalization of moving averages because now we say that we are creating more or less always also this historical time series by smoothing, and as we did it here in the moving average case, where we created here a smoothed data set, and now what we are doing is we are using our old created data set out of the original data, and we are then calculating an weighted average of the last data point we have, weighting with alpha. Alpha is a number between 0 and 1, plus 1 minus alpha, our last forecasted value for the data point t. Of course, we need these historical forecasted values. And where do we get these forecasted values? Well, of course, by averaging all historical data points. And then, of course, we need some initialization. And for this, we define that the first forecasted data point should be our naive forecast we already had. So we just define that the first data point should equal its forecast itself. So we define that y0 hat equals y0. Well, in a minute we will do this, of course, also with our data set. But we can also interpret this exponential smoothing in another way when we just manipulate our definition. And for this, again, this is the defining equation. And this we can rewrite since we just multiply this bracket, and then we see that it is 1 times the forecasted value minus alpha times the forecasted value, which we have here. And then we see we have here our alpha. So we can take this out of the brackets, and then we obtain that the forecasted value of t plus 1 equals the last forecasted value time plus alpha times the difference of the true data point yt minus our forecasted data point. And this is then our forecasting error in history. So we ask ourselves, well, how bad or good where we in history weighting this with our weighting parameter alpha, and this error we use for the prognosis for the next period. And this I've written down, of course, here. And well, quite often in lectures, we give you only just this definition or this definition of exponential smoothing. And maybe you ask yourself, and why we are calling this method exponential smoothing? Well, actually, this can be quite easy seen if we just iterate backwards our definition of our defining equation of exponential smoothing. Because let's start just with our definition, and then of course we apply for the former forecasted value, of course, also our definition. And then we can write for y hat t alpha equals y t minus 1 plus 1 minus alpha y hat t minus 1. And then here we have our factor 1 minus alpha. We end up with this part. And of course, again, here we have another forecasted value for t minus 1. And again, we put the next one in. We apply also for this forecasted value our definition, and iterating this in the end we will end up here. And how can we see this? Well, we just multiplying this bracket and these brackets, and so we obtain 1 minus alpha times y t minus 1 plus 1 minus alpha times 1 minus alpha is 1 minus alpha squared. And here we see that we have here an alpha and here an alpha. So this alpha can we take out of the brackets, and then we take end up here. And for this we then see that we obtain with this within this bracket here, iterating this backwards, that we obtain here our, let me take another color, and let me write down here a 1. So we have yt minus 1, and so on until y1, so our second data point. So this, and also yt0, and if we take this together, then this is our original data set. And this original data set is weighted with the factors 1 minus alpha weighting, 1 minus alpha squared, 1 minus alpha to the power of 3, and so on. And do you remember what kind of theories we have here? Well, I think you have seen this in your mathematics lecture, or hopefully also in your introductory course in statistics. This is nothing else than the geometric series. And this geometric series, of course, describes a growth process. And of course, when we are then going from discrete time, t equals 0, 1, 2, 3, 4, 5, 6, 7, to to that we move to the continuous time, and then this will go to our exponential function. For continuous time, we have the exponential function, and of course from this we then have the name of our method that we call it exponential smoothing, and of course I wrote it down here for you also. So this is also a widely used method for forecasting your data. So how can we interpret this parameter alpha? Of course, this is our weighting factor of our weighted average, and of course this can also be interpreted as the weighting of the convex mixture of these two values, so the data point itself and the forecasted data. And I think when you are introduced in microeconomics, in your utility theory, your convex preferences, then we talk also about a convex mixture of the amounts of two goods. And having a look at the definition of this equation, of course, we see that the higher this alpha, the closer we are at 1 with this alpha, then the relevance of the true last data point becomes higher and higher and higher, and the other way around means that we take a low smoothing, then we are moving more to the relevance of older data points, and this of course means that we have a stronger smoothing because we are looking more in history and not so much only at the actual data which we have. So having a higher alpha can then also be interpreted that we doing something like the taking the smoothing average with a high number of n, which would mean that we take the average of very much historical data points. Okay, so let's start also with some exercise and using our data and just applying an alpha of 0.3 or an alpha of 0.8. Again, we will go to Excel using our original data. And now we want our exponential smoothing. Well, and now we have to incorporate our definition. The first thing we need is, of course, the starting point that we use as the first forecasted value, the data point itself. So this will be then here equals 330. If we take here an alpha equals 0.3, what will be then our next data point, or what do I have to calculate creating the next data point? Please give me a hint. Alpha is 0.3. Let's go into our definition. And we know that our first, in quotation marks, forecasted value is 330. So what we have then is, let's say here, y hat 0 is 330. And we have, so to speak, y1 is 345. So then, of course, y hat 1 equals, if we take alpha equals 0.3, 0.3 times y0 plus 0.7 times y hat 0. These are, of course, the same, so we obtain y0. So again, 0.3 times y0 plus 1 minus 0.3 times our first forecasted value. And now starts the interesting part, because now we have here our forecasted value, and this of course now differs from the true value. So the next one would be then y hat 2 equals 0.3 times y1 plus 0.7 times y1 hat, and this will be then 0.3 times 345 plus 0.7 times 330. So here we can also then write that this is 330. And then we have put this in our formula, we can move this downward here. And then we move this just in the end of our time series. And of course, then we can make a forecast for 2023 Q1. And to end our lecture today, let's just have a look how our smooth data set looks like. And here again, you see that with this process, and since we have a low alpha, we have a quite strong smoothing of our data, and this here will be then our forecasted value. Okay, and then as homework, please redo our calculation for alpha equals 0.8. Then thank you very much for today. Oh, I have to